You ever stop and think about the invisible math that, holds our entire world together? Every single bridge you drive across, every plane you fly in, it was all built and stress tested inside a computer first using these super complex physics simulations. But what if I told you that a brand new type of AI is about to completely revolutionize how we do all of that?
So, here's our roadmap for this explainer. We're going to kick things off with the massive bottleneck that engineers are dealing with right now. Then, we'll meet an AI that's literally learning to think like a physicist. We'll watch it do a little warm-up and then see what happens when it goes head-to-head with the reigning champ of simulation. And stick around, because we're going to uncover its secret superpower before delivering the final verdict.
All right, let's dive right in. Now, to really get where we're going, you first have to appreciate the incredible tool that's been the absolute gold standard in engineering for like 80 years.
That tool is called the Finite Element Method, or FEM. And really, it's a genius idea. To figure out how a super complex shape is going to behave, you just break it down into millions of simple tiny pieces, a mesh, and solve the physics for each and every one. It's the undisputed champion for sure. But it has one massive weakness. And that weakness, it's the mesh itself. I want you to imagine trying to build an incredibly detailed model out of millions of tiny Lego bricks before you can even start your test. That's meshing. It's slow, it can take a ton of hands-on manual work, and for really complex 3D objects, it's a huge bottleneck that costs engineers a crazy amount of time and money.
So here's the big question. What if you could just skip the mesh entirely? What if an AI could understand the physics of a shape directly? Well, it looks like a new challenger has just entered the ring.
Say hello to the Physics-Informed Neural Network, or PIN. Now, unlike most AI models that just learn patterns by looking at a boatload of data, a PIN is totally different. It's actually taught the fundamental rules of the universe. I'm talking about the complex equations that describe how things like heat and stress and fluids actually work. It's all baked right into its core training. Okay, this slide really shows you what's so cool about the PIN's learning process. It basically picks a random spot on an object, makes a prediction about the forces at that exact point, and then, and this is the brilliant part, it checks its own answer against the laws of physics it was taught. It's literally grading its own homework over and over again.
So what this does is it creates this constant feedback loop. The AI's one and only goal is to shrink what you could call its physics error. The gap between what it predicted and what the actual equations say should be happening. It just keeps tweaking and adjusting itself millions of times until its answers line up perfectly with the rules of physics.
And this visual just perfectly illustrates the key advantage. Forget the Legos. The PIN does not need a structured grid. Instead, it learns the shape by sampling thousands of totally random points inside and on the surface of the object. It's a completely different and way more fluid approach to understanding geometry.
Okay, the theory sounds great, but talk is cheap, right? Can this AI actually solve a real-world problem? Well, researchers decided to start with a classic Engineering 101 test.
So here's the setup. A simple 3-meter beam, it's fixed at one end, and it has a steady load pushing down on it. The question is as simple as it gets. How much does the beam bend? This is a total textbook problem. It has a known perfect answer. It's the ideal first warm-up.
And the results? Just take a look at this. The blue line, that's the exact mathematically perfect solution. The orange dots, those are the PIN's predictions. They are practically sitting right on top of each other. The AI didn't just get close, it absolutely nailed it. The error was incredibly tiny.
So after that warm-up went so well, it was time to raise the stakes. Time for a true showdown against the reigning champion, FEM, but this time on a much, much tougher problem.
And here is our main event. We've got a metal plate fixed on the left, being pulled on the right. Now the real challenge here is that hole in the middle. In engineering, any sharp change in shape like that creates what we call a stress concentration. Basically, it's a hot spot where failure is most likely to begin. This is a classic test for any simulation tool. So, the stage is set. In one corner, you've got the industry standard, the trusted veteran, FEM. And in the other corner, the innovative, mesh-free AI challenger, PIN. Let's see the results. And this is where things get really fascinating. When it comes to accuracy, the PIN was amazing, less than 2% error compared to the FEM benchmark. But look at the speed. The PIN took about 24 minutes to solve this. The FEM simulation, it was way faster. So for now, on this specific problem, the champ holds on to its title.
So what we're looking at here is this really interesting trade-off. The pin gives you incredible flexibility because it avoids the whole mesh problem, and it offers what's called a continuous solution. That means you can find the answer at any point on the object, not just at predefined spots. But for now, when it comes to raw speed, FEM still wears the crown.
But if you think this story ends there, you are definitely mistaken. Because that straight-up fight doesn't really play to the AI's biggest strength. You see, the PINN has a secret superpower.
That superpower is called transfer learning. It's a really key concept in AI. Just think about it like this. Once you learn how to ride a bicycle, you don't have to start from square one to learn how to ride a motorcycle, right? You transfer your knowledge of balance and steering. Well, pins can do the exact same thing with physics problems. So to test this, the researchers took the pin that had already solved that first plate problem and they gave it a new, slightly different challenge. Like, say, a plate where the hole was a different size or in a different spot. Now, for a traditional FEM model, this means starting the whole time-consuming process all over again. But for the pin?
And this finding right here is the real game changer. Because the pin had already learned the basic physics of a plate being pulled, it could adapt to the new shape with a substantially reduced training time. It didn't have to learn everything from scratch. This is its true potential. Rapid, almost instant adaptation.
So, after this incredible showdown, what's the final verdict? What should you really take away from all this?
Let's break down the verdict. First up, pins are the real deal. They are absolutely accurate enough to compete with the gold standard, no question. Second, their mesh-free nature isn't just a gimmick, it's a huge advantage in flexibility. And yeah, while they might be the tortoise to FEM's hare in a single race, their secret weapon, that transfer learning, means they can adapt to new challenges almost instantly. This could totally revolutionize any design process that involves tons of tweaking and optimization.
So this leaves us with one last, really provocative thought. What we're looking at here isn't a replacement for engineers, but a powerful new partner. As these AI models get faster and more sophisticated, are we on the edge of a new era? An era where AI becomes our new digital physicist, working side by side with human engineers to design the future? It looks like the battle has just begun.